Imagine it's just the same class.
When we do linear combinations, we're essentially just adding those two wave functions.
Yeah.
And basically what we end up with is this. This is going to be a sigma, or 1s here. And if we look at the electron density, nucleus here, electron density, this is going to be high probability of finding it between the two nuclei.
Because that's where they overlap.
It's not overlap. I mean, this whole thing is an orbital here, and so we don't have overlapping orbitals. They overlap over here, but this is different than Valen's bond. In Valen's bond, we still retain a 1s, 1s. So what we end up with in Valen's bond theory is this. In Valen's bond theory, we have a 1s overlapping with a 1s. And this region of overlap would be higher probability of finding the electron cloud. In MO theory, we don't have this anymore. In MO theory, we have a whole new orbital. And this is going to be the sigma 1s orbital. But if we have the sigma 1s orbital, then we're also going to have this. You know, where we flip this one down. And so in this case, they don't add up.
So how is that orbital created, the sigma 1s? I guess that's where I'm kind of lost. You add the orbitals from atom A and atom B, and then that's how it creates sigma 1s?
Yeah, right. And so rather than having an overlap like this, we have this, a linear combination. So we add these two up and we get one new orbital. But this is two orbitals that we started with.
So in that case, the 1s from previous doesn't exist anymore. It's
No.
sigma 1s. Okay.
No, it doesn't exist anymore, but there's conservation of orbitals. So we have to generate one more orbital because we're taking two orbitals, and so we have to form two molecular orbitals. In this case, we're adding it to the psi squared, and so this would be plus plus. But if we take our psi and then square that, you know, as far as the probability function goes, this is going to be minus. And so we have a plus and a minus, which means we create an antibonding orbital. When we square this, it flips it over, you know, this. So what we end up with is getting a node. And so the way this looks is like this. An antibonding orbital would have one lobe over here, another lobe over here. It's because of how it adds. So this came from the plus, this came from the minus. So plus plus. And so it looks like this. So what happens is the repulsions begin to take over because the positive sees the other positive mostly. Here, the positive doesn't really see the other positive because there's electron cloud between the two. But since the electron cloud's missing here, and there's low probability here, most of the electron density is out here, then they call this an antibonding orbital. It's still an orbital. It still holds two electrons. It's just where the electron cloud is located. This would be bonding. This would be antibonding. So when I was looking at the orbitals yesterday, I was trying to figure out, are those antibonding or bonding by looking if there's some kind of node between the atoms which would result in repulsion. But here, I mean, this kind of stuff we don't really, deal with. And so when we're looking at the wave functions, probably be better just to look at the wave functions rather than antibonding orbitals when we have positive amplitude and negative amplitude. This is going to result in destructive, and so where they come into contact, you know, the positive amplitude cancels out the negative amplitude, and we end up with a node between the waves. So we end up with we have to use the color coding or the plus minus sign because we're looking at not sides usually, we're looking at size squared, you know, the probability distribution. Does that answer the question?
Yeah.
Were there other questions? Oh, the question is antibonding orbitals. Are antibonding orbitals orbitals? I think.
Yeah. If they're considered.
They're considered orbitals. It's just weird because for atoms, we just, you know, we just memorize the orbitals 1s, 2s, 2p, 3s. So we got a whole bunch of orbitals like this. For MO, we do the same thing. We just memorize it, sigma 1s, sigma star 1s. And so this would be like the 2s orbital here, you know. It would just be the next orbital up. It just so happens when we look at the electron cloud distribution for 2s orbitals like this. But the electron cloud distribution for this looks like this instead. So we just memorize it. Pick the next higher energy orbital, and then we just continue on up. All right. What we're doing today, though, are there any other questions? We can look at some molecular orbitals. We're going to build some acids tomorrow. We can look at the molecular orbitals for those acids. Or we could do simple ones. One simple one would just, in Spartan, if you want to see these, just build the hydrogen molecule. And hydrogen, you can just go up on that. I don't know how many unoccupied orbitals it will show. Probably at least 3. So hydrogen's going to be this for sure. Then maybe 3 more. There's probably a way of showing all of them, you know, all the way out to n equals infinity. All right. We looked at acid strength the other day. Let's look at base strength today. For bases, what do we want? We want a lone pair. This is for Bronsted. So we need a lone pair to accept a proton because protons don't have any electrons to donate to the bond. And so we need a lone pair for the electrons for the bond. And we want negative charge density. Negative charge. And it turns out the more localized the charge, the stronger the base. The strength will increase. And so let's take a look at some examples of this. Let's see which one I'm looking at. All right. An example of this would be something like. Actually, let's take a look. Just repeat one we looked at yesterday. Let's look at these two. These are acids, right? And so if these are acids, then the base would be if we lost the proton. So we could form the base. This would be ethoxide. And if this loses the proton, we're going to form acetate. So here. So just looking at the base strength, alone, you know, which one's a stronger base? Acetate or ethoxide, and why? Acetate would be the stronger?
Acetate's a stronger acid, so it has a weaker base. So
Yeah, but then,
oxide's got a stronger base.
yeah, the conjugate relationship we can always use, but that's not how we want to define it. We just, okay, let's not even consider the acid. Let's just look purely on base strength. Okay, and so I don't want to say, okay, acetic acid is a stronger acid, therefore its conjugate base, acetate, will be weaker. I want to just look at the structure of the bases and then figure out.
Ethoxide wants to donate electrons more because it has more electrons.
Ethoxide, well, ethoxide has 2, 4, 6 electrons, as lone pairs 2, 4, 6, so same.
But the carbon's more.
The carbon's more.
Doesn't it pull electrons to the carbon? Because the oxygen's pulling from the carbon.
Yeah, there are multiple factors here that we look at. When we look at bases, we look at localized versus what? Delocalized. When we think about delocalized, there's different ways, different mechanisms of delocalization. The most important method or mechanism of delocalization is resonance delocalization. And so here, this charge is localized on this oxygen, so it'd be a very hydroxide-like. This charge is not localized to this oxygen. It can be delocalized over these 2 oxygens because there's one more resonance form I can draw for this.
Mm-hmm.
And if I look at the hybrid is going to be -1/2 on each of the oxygens. And so I didn't draw the hybrid structure for this, and I didn't draw the other resonance form, but can you recognize them just by looking at it? Okay. The more resonance forms we can draw, the more delocalized for this. Can I draw any resonance forms for this? Is there any way to resonance delocalize that? No. And so that charge is stuck. And so this is going to make this a weaker acid. But there is another factor on there, and that is, you're right, the carbons are different. What's the difference between these 2 carbons? When I look at them. The oxidation state, that's good. The formal charge is the same. The electronegativity is the same, because carbon's a 2.5 in the electronegativity scale. But those 2 carbons are quite a bit different in terms of oxidation state. The carbon on the left, what's the oxidation state there? Now, you want to be able to do oxidation states in your head, at least.
+1.
+1. Close.
Are you talking about which carbon?
The left. This one.
Oh, you mean the right one?
The right one? It doesn't matter. That's all right. Tell me.
Okay.
The second carbon.
The left.
Oh, I meant this carbon here. The right one of this left structure. And so this carbon here is -1. This carbon here is -1. Yeah. This carbon here is
+3.
+3. And so what impact will that have on the negative charge? Well, the impact is, we frame it like this. This carbon here and this group is called an electron pusher. An electron donating group. And it's not really donating any electrons here because carbon really doesn't have any electrons to donate. So I just say electron density pushing group. And so it's pushing the cloud towards this oxygen, making this oxygen more negative or less negative? More negative, which means if it's more negative, and it's going to be a stronger base. Whereas this one is withdrawing the electron cloud, which means it's going to make this more positive. Well, this is a secondary effect. This is the inductive effect. what's more important is the delocalization. The resonance delocalization is going to be the biggest impact on this, and then secondarily, this carbon's electron withdrawer versus that carbon, which is electron pusher. And so we could see here. Now, if we do this, okay, so what did we say? This is going to be a lot weaker, right, acetate than ethoxide. Now, what happens if we do this? What happens if we well, actually, let's go back here. So here, ethoxide. In fact, ethoxide is one of the strong bases. It's not one of the strong bases you have to memorize, but it's a strong base. Acetate's a weak base. What if we do this? What if we put a chlorine here instead of a hydrogen? And so when you look at this part is the same in both of these. Now, when we look at this carbon, in organic chemistry, we call it the alpha carbon. The alpha carbon is going to have an impact on this. And so how does that impact it? Well, these two carbons are different. There's a difference here. Yeah, this carbon has a chlorine, which is going to pull electron density away. And so as it pulls electron density away, it's going to withdraw electron density from this group. Whereas this carbon doesn't pull. This is electron pusher, right? In terms of oxidation states, let's look at the oxidation state. The oxidation state on this carbon is what? -3. These two carbons are the same. These are +3. This carbon is at -1. So this is a -3, this is a -1. And so this one's going to push much more electron density. And -3 minus -1, well, -1 should push electron density too, but not nearly as much. And so we expect this one to be weaker or stronger? Actually, it's going to be a weaker base because it's getting electron density pulled more. And so that's going to delocalize the charge more. And so, in other words, pushing tries to localize the charge on here. Withdrawing tries to delocalize the charge into the structure. Okay. Well, let's take a look at this here. Now, we're going to compare two pushers here. This one, what's the oxidation state here? -3. This one is -2. So which one should be a better pusher, -3 or -2? -3. And so if we have a -3, that should be a stronger donator of electron density. Now we have some numbers here we can compare. And usually the bigger the number, the stronger. And so when we look at this, which number looks bigger?
The top.
The top one. And so does that make sense? Yeah, it seems to make sense. I mean, this is -3, that's -2. -3 is going to push more electron cloud this way, localizing electron density on those oxygens more, right? But you have to watch out because sometimes things aren't what they appear to be because here, looking at that, this is the number for acetic acid. Is this acetic acid? Is that no, that's not acetic acid, that's acetate. And so this is very tricky because they're telling us the number of acetic acid, but we're looking at its conjugate base. And then over here, so this is the number for this in acid form, so we have hydrogen here. And so it looks like acetic acid is stronger than octanoic acid. But that means if we have a stronger acid, its conjugate base should be weaker. And so it turns out this one is weaker than this one.
That's the base.
And so, but how can this one be weaker? This one has a -3, that has a -2. Why is this one weaker? Because this -3 is more electron rich than a -2. And it has to do with what? It has to do with this long chain here. Because this is -2, this one is -2, -2, -2, -2, -2, -3. And so the cumulative effect of this chain means that this chain is more electron rich than this single carbon here in the methyl. And so this is what we call a methyl substituent. This is a 1, 2, 3, 4, 5, 6, 7 heptyl substituent here. And so it says that chain length has little effect, but it has some effect. Because the effect is, the longer the chain, the hydrocarbon chain, the more of a electron rich or electron pusher it is. Even though the alpha carbon, when we look at that, alpha carbon here is -3, there's a -2, but then we have a beta carbon and a gamma carbon, etc. So we've got a lot of carbons in there. Yeah, to the chain. So the chain does have an impact on it. Seems to be. Okay, so let's look. This is one class of organic base. These are the, this is the acetate. This one's called octanoate. And so these are the OAtes, the acetate analogs. Another type of organic base are the means. These are ammonia analogs. So if we look at ammonia, now what happens if I do this? We'll do ammonia vs methylamine. So what's the difference between ammonia and methylamine? Well, if I look, I'm replacing this hydrogen here with a carbon. And so, well, if I replace a hydrogen and a carbon, a hydrogen, do you know what the electronegativity of hydrogen is? It's 2.1. Nitrogen's a 3O. And so if I look at the delta En of this bond, the delta En of this is 3 minus 2.1 is 0.9. Oops, I miscalculated it earlier today. It's 0.9. Carbon's a 2.5, right? Nitrogen is a 3.0. So delta En here is 0.5. And so what do we do with these delta ENs? What we do with these delta ENs is we set up polar bonds. So when we look at the polar bonds, it's like this. If carbon is more electronegative, then it's going to suck more electron density away, right? Because this is an EN of 2.1. This has an EN of 2.5. And so what that means is that carbon is going to be more electronegative, so this bond isn't going to be as symmetric. In other words, we're going to build up some negative charge on the nitrogen, but over here we'll build up more negative charge on the nitrogen. We're going to build up more negative charge on the nitrogen because hydrogen isn't going to pull as much electron density. But this is a little bit of nitpicking because we say that carbon and hydrogen have essentially the same electronegativity. The difference between 2.1 and 2.5 is minimal. And so this is why these are called amines. These are called amines because, you know, if you have a carbon, you have a hydrogen, it doesn't make much difference. This is going to be basic, this is going to be basic, just like ammonia. Now, I just want to know which one's going to be more basic. And so what do you predict? Which one will be more basic? You would predict ammonia would be more basic because if there's a tug of war between nitrogen and hydrogen versus nitrogen and carbon, hydrogen's a weaker opponent. Hydrogen's a weaker opponent, then nitrogen's gonna build up more of the cloud. Carbon's a little stronger, so nitrogen doesn't build up as big of a cloud. Does that make sense? So we use this kind of argument here, but let's take a look at the numbers. Would you say that sounds good to you? Or do you have a differing view? On the other hand, when we look at the structures, we also look at the oxidation state. And so let's analyze it like we did this one. We look at the alpha carbon. In this case, we're just going to look at that left position. And we saw that these two carbons are different. Because if we use electronegativity here, the electronegativity of carbon is 2.5. The electronegativity of carbon is 2.5. Is that right? Both of these should be the same. Well, it's not right, because the electronegativity of carbon depends on the charge on the carbon atom. So for example, a carbon with -2 is going to be at a different electronegativity than the carbon at -3. And so electronegativity is very tricky to use. And so this is why, you know, on the past exams I've given this question: which one is more electronegative? Fluorine versus fluoride, are they the same? No, they're totally different. Which one's more electronegative?
Fluorine.
Fluorine. And so we have to be careful in our use of electronegativities, but this sounds reasonable. But there's one other thing, and this is the other thing I noticed. When I look at this, you know, I didn't even really consider electronegativities necessarily. I looked at the substituent. You know, what I'm talking about in terms of substituent is this. I have this, and so right now I have a hydrogen substituent. So I'm going to remove the hydrogen substituent and replace it with a methyl substituent. And so there's a difference between hydrogen and methyl. And the way we think about this is we think of it in terms of electron rich, or electron donating, or electron pushing, versus electron poor, that is electron withdrawing, electron deficient, let's say, or sucking, or taking electron density. And so when I look at these two groups, the other thing I look at is, you know, are they the same in terms of, well, if I look at a methyl group like this and compare it with a hydrogen group, one thing I look at is the oxidation state. What's the oxidation state of the methyl over here? The oxidation state of the methyl here is different than the oxidation state of the methyl here. The methyl is the CH3. So we're looking at the substituent. We have a methyl group versus a heptyl group, the substituent here. And so when you look at a methyl group, what do you think? Well, when I look at a methyl group, I think electron pusher or electron withdrawer.
Sure.
I think of electron pusher. And when I look at the oxidation state, what's the oxidation state on carbon? The oxidation state on this carbon is 2, 4, 6, 7, -3. No, actually, no, 2, 4, 6, sorry, not -3, minus 2. So the oxidation state is -2, which means, hey, that's kind of electron rich, that's going to be electron pusher. And so when I look at this, I see, oh, that's a -2. And the oxidation state on this hydrogen is +1. And so if I were just to look, if I were to ignore the electronegativities and just look at that, which one would you say is more basic? The one on the right. If I were to look at electronegativities in delta En, I would say the one on the left. And so which is it? And so this is what we got to do, because, you know, to calculate delta En, anybody can do that. You just teach somebody how to read the table, and just look it up and subtract the numbers. to calculate the oxidation state, anybody could do that, right? Anybody, once you learn the rules. What the hard part is interpreting the numbers. Not everybody can interpret the numbers. Now, how do you interpret the numbers? The way we interpret the numbers is this. We memorize some experimental facts. We have to understand some factual data. And we got to see how that compares to factual data, because the factual, whatever theory we come up with, it has to agree with experimental facts. If the theory doesn't, like the Bohr theory, then it's abandoned. And so anyway, we're trying to analyze the structure of these things. And so let's take a look at some data. And so I'm going to go to Appendix D here, and we'll just cut across. Appendix D has numerous data tables. Here. This is a base. These are for Bronsted bases. Base tables. Here is, here's ammonium. And so here's the number. Now this number is for ammonia. This isn't for its conjugate acid or anything else. This is Kb. B stands for base. This is 1.8 times 10 to the minus 5. So we use that as a reference point. 1.8 times 10 to the minus 5. And then let's look at methylamine. Methylamines here. So we replace the hydrogen with a methyl group here, and we get methylamine. That's 4.2 times 10 to the minus 4. Which one's stronger? Methylamine. And about how many times stronger is it? It's 10 times stronger, which tells me what? Which tells me that did this electronegativity analysis really work? No, it tells me this. It tells me that this methyl group having a -2 oxidation state here, this is electron rich. This methyl group being electron rich is pushing electron density to the nitrogen, making that nitrogen more basic. And so because of the substituent here, this turns out to be more basic. Okay. All right, now let's do this. Let's try to apply this to this. Let's go to ethylamine. Ethylamine would have 2 carbons. And if I look at ethylamine, well, let's apply the same kind of analysis to ethylamine. What's the oxidation state on this carbon? Well, this one's -2. This one is going to be -1. Because the oxidation state here is -1. So now we go -2 carbon versus -1. -2 is better. -2 should make a more powerful base. But the other thing we have to do is we have to consider, this is the alpha carbon, we also have to consider the beta carbon, and the gamma carbon, if there's a gamma carbon. And so when we look at these, we see that this beta carbon's what? -3. Whereas over here in the beta position would be a hydrogen, a +1. Now when we look at this, which one looks better? This one looks better. And the chain length has a small effect or impact on things. So let's see, did our prediction come out right? And so let's compare this. We're going to compare methylamine. Methylamine is 4.2 times 10 to the minus 4 versus ethylamine. Ethylamine here is 4.3 times 10 to the minus 4. So which one came out stronger? Ethylamine came out stronger. But 4.2 versus 4.3, much of a difference? No, but still slightly stronger. And so this hydrocarbon group, whereas if we go to propylamine, what do you think? Now we're getting, the gamma carbon, that's going to have less impact. Unfortunately, we don't have data for propylamine. But we can do this. We can go to dimethylamine. If we go to dimethylamine, and then we stick on 2 electron-rich methyl groups. Onto the nitrogen. And so we'll remove another hydrogen, put another methyl group. Dimethylamine, what do you expect here compared to methylamine? More basic or? More basic. And so let's take a look here. Dimethylamine, 5.9 times 10 to the minus 4. Methylamine, 4.2. So it is more basic. Trimethylamine, what do you think is going to happen with trimethylamine? More basic too. Trimethylamine, 6.3. Actually, trimethyl, where is it? Trimethylamine, if you look at that, it's actually weaker. It's weaker. Why would it be weaker? We would expect it to be stronger,
Because maybe the lone pair on the nitrogen is not if you draw the structure.
Well, there are other factors that we have to consider, obviously, because of this. Because when we go from methyl in -4, this is actually quite a bit weaker. And one of the other factors that we have to consider is this. One of the other factors we have to consider is a methyl group is fairly small, but if we put a fairly large group on here, like this, this group is called a T-butyl group. If we put a T-butyl group on there, like this, then it has what we call steric hindrance. That is, this bulky group inhibits acids from coming to attack this, which decreases its basicity, even though you would expect it to be comparable. And so this one It could be, maybe it's due to steric hindrance, having 3 methyl groups there. Like this. But looking at it, it looks like about 10 times weaker, 6.3. So we go from dimethylamine, 5.9 times 10 to the minus 4 to 6.3 times 10 to the minus 5, about 10 times weaker. And so this one we have to think about as far as what does it. And so what we're doing right now is we're just trying to build some correlations here. In other words, what we're trying to do is we're trying to come up with some kind of pattern that we can find and then understand that pattern. That's what we're going to do tomorrow in lab. We're going to take a whole bunch of data like this and see if we can correlate it with some kind of structural feature or some kind of pattern. And this is what we're going to do here. And so this is our initial step, just looking at the data and seeing what kind of patterns we can generate. So we'll continue with this, but trimethylamine, we'll think about that, maybe come up with a reason why it would be 10 times weaker with the third one. We expect it to be stronger. All right, let's see some of these others to see what we can do. For example, codeine. If we look at codeine here, so we're going from, okay, we go from ammonia here. Let's take a look at codeine and then see what we can determine. Codeine is also an amine. And let's take a look at the structure of codeine.
Don't take too much of that.
Yeah.
Mess up your brain.
Codeine's a painkiller. Codeine's amine because it has this group. Now, in organic chemistry, this nitrogen is bonded to wet over here. Well, this is a shorthand method. This would be a carbon, right, at the intersection. So this nitrogen bonded to 3 carbons, like trimethylamine or something like that. But we think about the strength. In this case here, how many hydrogens are bonded? Well, if I have a carbon here, what is the hybridization on that carbon? Looks like sp2 because it looks like 3 things are bonded to it. But in this shorthand structure, there's a hydrogen bonded here that they don't show. I know that because carbon likes to form 4 bonds, and they're only showing 3 bonds here, so the 4th bond's got to be the hydrogen. Over here, this carbon here is only showing 2 bonds, so there has to be 2 hydrogens there. Those are hydrocarbon-like hydrocarbon-like groups. And so I have 3 hydrocarbon-like groups. All those 3 are contributing electron density to this nitrogen, making this more basic, right? So we'd expect this one to be more basic, but let's take a look at the number. Oops. Okay. Here. What's the number for codeine? Codeine turns out to be weaker than ammonia. You see that? Weaker. And so, well, maybe we need more observations to see if we can find a pattern. And so let's take some more observations. Well, we're going to go to let's go to this. Not on this chart here, but we'll do something like this. Let's look at this bottom one here. We'll look at hydroxylamine. Maybe we need to make it a little simpler. If we look at hydroxylamine, we're going to replace the hydrogen with an OH group. So replacing the hydrogen with an OH, will that make a stronger or weaker base? This should make it a weaker base. Why? Because this should be an electron withdrawing group. An electron withdrawing group is going to make the nitrogen less basic. So hopefully that works. Well, and we see hydroxylamine compared to ammonia, this is about what, 4 orders of magnitude? 5 orders of magnitude? Well, let's say just 4. This is like 1,000 or 1,000 times weaker, maybe 10,000 times weaker, 100 times. And so having that hydroxyl, that's going to make it much weaker. And therefore, I mean, this is still considered an amine, but once we get to something like this is no longer considered an amine. Amines are weak organic bases. This one isn't basic at all, really. And why is that here? So this is still considered an amine. This one is no longer considered an amine. Do you see why? Because if this is like 1,000 times weaker than ammonia, this would be like, yeah, much, much, much weaker. It would be so weak that it's not really a very good base. And so this is extremely weak. So this is not an amine. Well, these are all amines here, right? Look at the name. Do you see? They all end in amine. So these are all amines, or amines, amine. And so what we're going to do is we're going to analyze some of these structurally and see if it makes sense. And so we're going to go to aniline. When we go to aniline, aniline is the common name for this, but essentially it's ammonia. And this ammonia, what we're going to do is we're going to stick a C6H5 group on it. The C6H5 group looks like this: 6 carbons in a ring. You got the 5 hydrogens. This is what it looks like. And do you recognize this molecule? This looks like benzene. Benzene is a substituent. It's called phenyl, not benzyl. This will be phenyl. Phenyl in organic chemistry is given this symbol. So phenyl, what would you say? Is that going to be an electron pushing group or an electron withdrawing group? Is it electron pushing or electron withdrawing? Well, if we look at the oxidation state, what's the oxidation state on this carbon here? No. Not 0. +1. If I have a carbon +1, what do you think? That's more electron withdrawing or more electron pushing? More electron withdrawing. Even though this is a hydrocarbon type group, it looks like to be an electron withdrawing. But this is like and so normally hydrocarbons are electron pushing, but not this one. This is going to be more electron withdrawing, and this is going to be actually. Let's take a look. Does it make sense? Because let's compare the strength. If we compare the strength of ammonia versus aniline, look at the difference. Aniline is how many times weaker? Aniline looks to be about 5 orders of magnitude weaker, 10 to the minus 5 versus 10 to the minus 10. So aniline is considerably weaker. Well, does this explain all of it? No. Aniline's special because, this is special. This is not like a normal alkene. An alkene has a carbon-carbon double bond. We call them alkenes. Alkenes, typically they're electron pushers. But this has an interesting network. It has double, single, double, single. When we have this type of arrangement, it has special properties, and we call it give it a different name. This class of organic compounds is called the, when you have alternating single and double bonds, we call it, Because a lot of these compounds have a nice smell or aroma to them.
Aromatic.
Aromatic.
Yeah, this is aromatic here. And because of this network, there are a couple of things we can visualize. One thing is there's a delocalized pi bonding network. All the p orbitals are lined up here. And so the p orbital can accommodate more electron density, so we can delocalize it that way. Another thing about this is this. Even though it doesn't look like it, what can happen is this. We can actually delocalize the electrons into the ring by doing this. We'll put this sp3 lone pair into the bond, and we'll make a pi bond here. So we'll convert this nitrogen to sp2, we'll form a pp pi bond here. But that means too many bonds around carbon. Carbon doesn't want 5 bonds, so we'll take this pi bond, break it, convert this sp2 carbon into an sp3 carbon, and put the lone pair on that. And so we end up with a structure that looks like this. So everything still has an octet, okay there, but the formal charges are no longer 0. You know, in aniline, all the formal charges are 0. When you look at the formal charges here, what are the formal charges? Yeah, nitrogen's +1. And this carbon would be -1. And so now we have some formal charge, which means these aren't equivalent. You know, this would be more stable than that. But it turns out that we can generate more resonance forms than just this. And so additional resonance forms that we can generate would be, actually, can you figure out another resonance form? Another resonance form would be, well, if we go backwards, here and then here, we end up with this structure. I don't want to end up at that structure. And so try to figure out another resonance form for this. The atoms can't move. The atoms have to stay put. And so you can't move this amine group around the ring. You can't move the hydrogens either. The only thing you can move are the electrons when you're doing resonance. And so what's the other resonance form look like?
Like the opposite. The double bond will be on top for the benzene and the switch.
Well, not exactly the opposite, because we would just, we wouldn't jump the electrons that far. I mean, we could jump these over here, then we'd have 2 negative charges. And so I wouldn't do the opposite next. Does somebody have it?
Move the double bond one left, rotate them.
Yeah, we could rotate the double bonds, but what we do is we convert this sp3 into pi, and then convert this into a lone pair. And so the next resonance form would look like this. Or now we have the positive charge over here and the negative charge over here in this position. Okay, are there any others we can come up with? Do you see?
Let's keep going.
Yeah, you just keep going around the ring. If we go around the ring, then we'll make a double bond here, Oops, never got this one. We'll make a double bond here, which is gonna kick this one out onto the carbon here. And we end up with this structure. Okay, any others? The last one would be just to revert back to the original. And so altogether, there are going to be 4 resonance structures. The more resonance structures, the more delocalized the electron density, even though these aren't equivalent resonance forms. And so this means that aniline is going to be a much weaker base. In other words, this ring, this aromatic ring, has a net electron withdrawing effect on this amine here. All right, so we did we looked at codeine. Come back to we looked at diethylamine, dimethylamine, ethylamine. How about hydrazine? We haven't looked at hydrazine yet. So let's take a look at the hydrazine. What do you think for hydrazine? Well, let's take a look. If we go to hydrazine, we're going to do this. We're going to replace the hydrogen and put another amine group on here. And so this is like 2 ammonia stuck together. It's hydrazine. Now, will hydrazine be a better base or worse base than ammonia?
Worse.
Well, looking at the numbers here, the numbers show it's going to be worse. It's like 100 times worse than ammonia. Now, why is it? Does it make sense? And so, one of the things is we look at this group here. I look at this group and take a look at the oxidation state. What's the oxidation state on this? Nitrogen. Now -1.
-2.
Let's see, 2, 4, 6, 7. It's supposed to have 5. So -2 is correct. -2, you'd expect that to be what? Electron rich? That seems fairly electron rich, doesn't it? So if this is electron rich, then this seems to be an electron pusher, correct? Shouldn't that be electron pusher?
But the other one's the same.
They're both the same, but we're just comparing it. If I had a hydrogen here, this is the way we analyze it, because what we're doing is we're substituting. We're substituting, these are called substituents. So we're going to substitute hydrogen with a amine. And so we're comparing hydrogen to this. Now this one seems electron rich, so it should push. If it pushes electron density, that means it's going to be more basic. And so this should be more basic. Hydrazine should be more basic, shouldn't it? Not less basic. Why is it less basic? Why is it less basic? Well,
It's not polar.
yeah. One of the things is it's a nonpolar bond. It's a nonpolar bond compared to, now what we have to do is we have to compare it to what? We have to compare it to ammonia. When we compare it to ammonia, we see this. When we compare it to ammonia, this is a much more polar bond. Why? Because nitrogen is much more electronegative than hydrogen. And so nitrogen is going to pull, hydrogen is going to lose that electron density more. And so what that means is this is going to build up more negative charge than this, making this one more basic, because hydrogen's weaker than nitrogen. But wait a minute, didn't I say something like electronegativity isn't that big of a factor? Am I not just contradicting myself? Am I just making these arguments up as I go along to fit the data? This is called ad hoc analysis? Ad hoc analysis is you look at what you need to do and then you make up some argument that's consistent with what you need to do each time. So in this case, you use electronegativity. In the previous case, you have to ignore the electronegativity entirely because it just doesn't work, right? Well, actually, it's not. It's not so arbitrary because we just did the same thing. We just did the same thing with this. Do you remember this? Is this? This is hydroxylamine. Hydroxylamine, well, we go, hey, oxygen, hey, this is -2. That's the oxidation state on that oxygen. If the oxygen is -2, isn't that electron rich? Isn't that an electron pusher? It's -2. I saw a -2 before. We saw -2 in ethylamine. Remember ethylamine? Ethylamine was -2 also. So we have ethylamine here. Ethylamine had a -2 here. And so this is -2, this is -2, making these two the same. These two should have the same base strength. In other words, hydroxylamine and ethylamine should be equivalent in terms of base strength because both of these are electron rich. This oxygen, this carbon is electron rich, both electron pushers. Is that the case? No, not at all. That's not the case. It's not the case. Why? Because the numbers, the numbers are the numbers, but you have to interpret the numbers. So a -2 on oxygen, we already know -2 on oxygen, does that make oxygen electron rich? So for example, if my gas ran out, the gas ran out, there's no more natural gas, I got water here. Water, oxygen's -2. Well, oxygen is -2, that's got to be electron rich, therefore it should burn. And so if I run out of methane, I'll just burn the water instead in O2. Is that going to work? No, it's not going to work at all. And so what we have to do is, there's a lot of stuff to keep track of, but what we have to do is we have to compare. This is not electron rich, even though it's -2, but this is electron rich. This is a carbon atom, not oxygen. And so being able to calculate the numbers doesn't mean anything because you have to be able to interpret the numbers as well. And interpreting the numbers is the hard part. And interpreting the numbers is it's one thing. Like I think I mentioned maybe 3 times, can you burn water? Can you burn water? Can you burn water, right? To illustrate that, -2 on oxygen's not electron rich. But the thing is, memorizing what somebody else says, do you guys remember when I said, can you burn water before?
Probably the morning class.
All right.
I think I remember something.
You remember something like that? But did it really stick? It doesn't stick. It doesn't stick because the way you really learn things is you have to come up with it yourself. It's not memorizing what somebody else says. I can come up with a nice little conclusion. You can't burn water. Oxygen's not electron rich. But it doesn't really stick unless you come up with that conclusion yourself. And the way you come up with that conclusion yourself is you take this whole jumble. This is a whole jumble of data, doesn't it? This looks like a mess. And you take this mess and you organize it. And when you organize, and the process of organizing the information yourself really makes it stick in your memory, And so this is kind of what we do all the time in science. In science is it's called data reduction. You got this whole mess of data, and the process, the learning process, is the organizing of it, is the trying to figure out the correlations. So we're going to be taking data tomorrow in lab. We're going to be taking down a whole bunch of numbers. These numbers are going to look totally random, and then we're going to try to come up with some sort of correlation. We'll see. But anyway, this is it. What we have to do is we have to take the numbers and then match it with actual data. The actual data tells us, is our theoretical thinking, are we on the right track or not? Because if our analysis of this does not agree with the data, does that mean the data is wrong? Or does that mean our analysis is wrong? It means our analysis is wrong. And so we do this. But just because our analysis might agree, we might not have seen something where there's a violation. So we have to be careful. But in this case, these two are different. When I look at this, is this nitrogen just as electron rich as this oxygen? No, but I treat this nitrogen kind of the same way. This is not really a good electron donor. Nitrogen is not a great electron donor because even though it has a -2 charge, it's kind of happy as is. Although, something like ammonia, does this burn? Let me ask you that. Does hydrazine burn? Yes, hydrazine burns. You might have heard of hydrazine before because hydrazine is actually rocket fuel, right? Whereas water is not rocket fuel, so there's a big difference between these two -2s, the -2 here versus -2 in water. So if you ran out of hydrazine, well, you might think you might be able to use water, but unfortunately you still can't use water as a substitute. Ammonia you could use because ammonia is even more electron rich. And so what we do is we try to marry the factual knowledge. A lot of people say, I don't want to memorize, because we just look it up or Google it, but you have to memorize. You have to memorize some reference points. So I ask you to memorize certain reference points like wavelength of red and violet, and energies, bond energies, this type of stuff. And so we're going to try to, correlate some numbers here. And so now, does it make sense here, in terms, because nitrogen is quite electronegative. So this is why it likes to hold on to those electrons. But looking at this is the way we'd argue it. Yeah, hydrogen should be a weaker base than ammonia because this nitrogen is going to pull more electron density than the hydrogen would. We'd have that. Whereas here we're comparing methylamine with ethylamine. Both of them are carbons. Both carbons are electronegativity 2.5. And so here, for sure, we can use the charge telling us, But then even when we do use the charge, we have to worry about the chain length. And so what we do is we start to look at all the factors influencing the base strength. Well, let's go on to the next one. Hydrazine is known as a diabasic base. It could accept 2 protons. So if hydrazine accepts 1 proton, what does that do to its base strength? And so thinking in the same vein, as far as analysis goes, we would replace, so we just look, okay, we have the amine type unit here. We don't have to have 2 hydrogen atoms. And then what we're going to put is like ammonium type ion here. So it accepted 1 proton, so it forms this kind of ammonium type unit. When we put this on here, what's going to happen to the base strength? The base strength is going to go up or down? Did it go down? Yeah, the base strength is going to go down because now the nitrogen is,
Pulling more.
going to pull more. In fact, the nitrogen with a positive, this is a formal charge, positive formal charge. Which means it's going to pull electron density. And you can see, take a look at what happened to the base strength. It went down like 9 orders of magnitude. 9 orders of magnitude, like a billion times weaker. A billion times weaker of a base. All right. Isoquinoline here is quite a bit weaker. So there's a ring structure. Morphine. Actually, let's take a look at morphine compared to codeine here. So this is codeine. Let's take a look at morphine here. Did I just bring up codeine again? Doesn't that look like codeine? It looks like codeine. This is codeine. This is morphine. The same thing?
No.
No, H3C.
Nothing
and H1.
comes out. That's the
Oh, right. Morphine has a hydrogen here. Codeine has a methyl group here. Changes a little bit. Otherwise, they're the same. And so when we look at the mean part looks the same. And so for some reason, and when we get into rings, things get a little bit more complicated because this is 5 rings. You have kind of this aromatic ring up here, but then you have these are called aliphatic rings, which aren't aromatic. And then you have these other functional groups in here, which are kind of similar. You have that. And so there are other factors that influence. When we have rings, there could be bond strain and other stuff that can impact the basicity. And so we try to look for purity, methylamine. So those are some bases, and the bases, that's it for the bases that we have here. There are other bases too that we can consider as well, which we'll look at later. So we look at some of the factors that influence basicity, and then let's try to analyze some bases now. So let's go back to this PowerPoint. See if we have enough, so we can make some predictions. Yeah. All right. Let's take a look at these 2 bases and you tell me which one is stronger. Ammonia or bromamine? Which one's a stronger base? Ammonia or bromamine? Okay, why is bromamine a stronger base?
The bromine sucks all the electrons towards itself.
Yeah. Yeah, bromine's much more electronegative than hydrogen. It's going to suck electron density away from the nitrogen. Correct? What about the numbers? Well, these numbers are kind of funny. These are P, which are power functions. And so the smaller the power function, the bigger it is. And so this is actually bigger number. And so this is a stronger base. And power functions are orders of 10. And so this is 3 orders of 10, or 3 orders of magnitude bigger. This is 1,000 times stronger than this. All right, ammonia versus methylamine versus ethylamine. We did this. Which one's going to be the most basic? Ethylamine. Okay, it's a chain link. Here we can see it. If we look at ammonia and methylamine, when we look at the power functions, they're pretty much the same because of round-off error. They're very close to begin with. But we expected methyl to be stronger, and it was. Methylamine was stronger, and ethylamine is even stronger than that. Okay. Do you see what's happening here? This is, on the top is aniline, or phenylamine. And what we have here is, this is the organic shorthand structure. And in organic chemistry, we label the carbon positions in this ring differently. So for example, this is called the ortho position here. So we have a lone pair in ortho. And the next position over here is meta, ortho, meta, and the final position here is called para. And so here we have a lone pair in the ortho position, and then it skips the meta position and goes to the para position, and then it skips this meta position and goes to the ortho position here. And so we see that when the negative charge density is delocalized into the ring, it ends up on the ortho and the para, but not the meta. Well, that's going to have an impact on things. Now look at these two structures and tell me why there's such a huge difference. This is 6 orders of magnitude. So one of these is 1,000,000 times stronger, or one of these is 1,000,000 times weaker than the other, based on power functions. And so can you say why? Which one is stronger, which one's weaker? And then, so let me give you a minute to think about that, unless you can see it. But they kind of look the same, don't they?
Maybe cycle back to
What you're saying was that we're recording.
For 6 hydrocarbons, second
No, I'm saying what was the question?
So the carbon
It's not the question, it's the answer.
higher oxidation state, so it's like more electrons.
Yeah, I would.
I don't even know why I came to class. Yeah, that's a good one. I'm just seeing the real one. Well, I thought I did one.
I think this is oxidation.
We just can could be which is now. Yeah. You are 80. We're 80 today. Have you heard of the Drake equation? So according to some, there's at least 10,000 intelligent civilizations in this galaxy. How did you know that? Because we're alone or
Right.
pretty interesting.
So what we have here is we have 2 rings. These are 6 carbon rings, but these rings behave totally differently. One is an electron pusher, the other is electron withdrawer. Which one is the electron pusher? The one on the left or the one on the right? On the left. This is an electron pusher ring, however this is electron puller ring. Why is that so? Why that's so is this one's just a normal hydrocarbon. And when I look at this is sp3, sp3, all these are sp3 carbons over here. And if we draw the structure of that, the one on the left, this is what it will look like. It's not going to be a flat ring like benzene. It's going to look like this. There's got to be hydrogens here, so we need 2 hydrogens. I'm not going to draw this totally 3D. Actually, in organic chemistry, you get good at drawing these. I should try to draw more accurately. Well, anyway, when we look at this carbon and compare it to, what's the oxidation state on this carbon here?
Zero.
This is 1, 2, 3, 4, 0. Versus the carbon on aniline, we had it as +1, but there's going to be a huge difference here. And the huge difference is, okay, this is 0, this one is -2, -2, -2, -2, -2. And so we got this whole ring of -2 carbons here, which is going to make this group electron rich. And so this ring is electron pusher, whereas this ring is an electron puller. An electron puller because we could delocalize the charge density in the ring, and this +1 as well. Okay. And so there's going to be a huge difference in basicity. This one's going to be a million times more basic. Now, let's take a look at these. These are what we call substituted aniline here. We'll put a chloro. This is called parachloroaniline. If we put a chloro here, does that help basicity or hurt basicity? That hurts basicity. Why? It pulls electron density. And so if I look at this resonance form here, if I have a chloro attached, that chloro can suck some of that negative charge towards it, helping delocalize the structure even more. And so this would be less basic. The same thing with the ortho. The ortho position also has negative charge density there. However, meta, if I put the chloro in the meta position, it doesn't make much difference. Because in the meta, we don't have the negative charge enough there. And so we'll look at some more substituted bases and try to understand this a little bit.